So here we have a few pictures of kind of our progress we've done so far. This first picture here is a shot of an oscilloscope from our original prototype from our previous design class. We had built a small prototype to run a very tiny DC motor. And here you can see we have our sawtooth wave, which is created internally inside the PWM chip. And this voltage level here is set by the voltage, the 5K throttle potentiometer. And that basically gives these intersection points to create this modulated waveform, which will control our motor speed, basically. If you raise this and lower this, that will change the duty cycle of our output waveform, therefore changing the speed of the motor. And over here we have Nick working on the front of the car. This front bumper was bent, so we decided to remove it because it was kind of hindering some stuff. And this is our motor, basically disassembled for painting. We're primering it so we can get it all painted. And here we have the batteries that were donated to us.
Alright, so we went over our sponsor, which Bill's here. Hooray. That's Bill Schlanger from Electric Blue Motors. We have our team advisor, Dr. Kibble. We went through and covered all this, so just keep it short.
Okay. The references were basically the pictures that we got off the Electric Blue website. We also pulled Dr. Kibble's off of the NAU website, and now we can actually go into our website.
We just wanted to kind of show what we've done so far with our website. I'm not going to go too far into it, but this is our basic layout, and we wanted to give credit to all our sponsors here at the bottom. So we just encourage people to go check it out. We're going to be continually updating it with news and different things we're doing.
So in closing, we would just like to thank all of our sponsors, Electric Blue, for donating the project and the facility to work on our Land Rover controller. Universal Power Group is the company that donated the batteries for us. Highway 85 Creative is doing the logos, which should be shipped here today or tomorrow, so we hope to have those on the car this weekend. And then APS and Northern Arizona University for the grant. And we'd just like to thank all the professors that showed up, Bill and Raytheon, the members from Raytheon.
Questions? Dr. Kibble.
When did you choose those particular batteries, that type of battery?
Well, the Land Rover is a fairly heavy vehicle. It sits at 4,400 pounds before the engine we yanked out, and in order to move such a heavy mass, we needed a fairly large battery. And these batteries in particular are AGM 250 amp hour batteries. And with some real rough calculations, we're expecting that the Land Rover to go anywhere between 25 to 40 miles per charge. So we inherently need a fairly large battery bank. Generally speaking, for regular cars that weigh about 2,500 pounds, you want to go with a battery pack that's 144 volts and about 100 amp hours. And that'll give you a range of about 50 miles. So since we doubled our weight, we're going to have to more than double our battery bank. And this is something that Universal Power Group is more going to donate to us.
Okay, so did you choose AGM over like lithium?
Gel batteries? From what I was told, we've been using, or Electric Blue has been using gel batteries, but from what I'm told, that AGM batteries should perform a little bit better, so we decided to go with that. Universal Power Group does have an equivalent gel battery, but they also concluded that AGM should perform a little bit better. That's a traction battery. And you can also go with lithium, but that's just way too expensive, and I don't believe there's any company out there, especially now, that's willing to donate a lithium battery pack to move a Land Rover. Ryan?
Okay, so this is somewhat outside the scope of your project, but is there going to be any way such that like braking the vehicle will feed back into the batteries or feed back into the system in any way, or something similar to that?
Like current going back through the motor?
Yeah, so instead of braking, just wasting the energy and heat.
Oh, you mean like more like regenerative braking?
Yes, yes.
The way that the DC brush motor is set up, it cannot handle to be run as a generator to feed back the current. It is possible the way we're doing it. We only have one MOSFET on the low side of the motor, if you set it up in an H-bridge style fashion so that the motor is set in between, kind of like a Wheatstone bridge, but except transistors, and then instead of that center, like R5 resistor, it'd be the motor right there. You can do it that way and configure it. I believe it's a series wound motor that can give you the regenerative braking if you want to do it in this DC stuff. But for cost purposes, we've decided to go with just one MOSFET or 4 MOSFETs on the low side to drive this motor.
So, curiosity about the failure modes. What do you anticipate, and how do you intend to make sure it fails in a known manner?
Well, what we're really trying to prevent is latch up in the MOSFET. And when it comes to these MOSFETs, they generally fail by shorting out, and that's what we want to prevent. And that's where our further research needs to take place, where we need to prevent the latch up. Generally speaking, from what I've learned so far, is you want to put Schottky diodes that tie, that are reverse bias, that tie from the output of the MOSFET driver to ground, and that are reverse bias to the output of the MOSFET driver to your power supply. So that way, you prevent your your gate voltage to exceed any of the power rails on your drain or your source on the MOSFET. So that way, it'll bleed the extra power from the MOSFET driver either to your power supply or to your ground, depending on whether it goes too high or too low.
It's been a while since I've looked at power components that are available on the market. But I'm curious if you looked at IGBTs at all?
We have, and Jeremy, someone else want to answer that?
Okay, I'll do it. I'm there. Okay, so we actually went through and found about 7 papers, was it? Yeah, there were 7 papers, and it actually went through, and the first one was basically, which do you determine between an IGBT or the MOSFET? And basically it was if we had there was a certain voltage range, if you were using a certain voltage range, you were going to use an IGBT, or the other range would be the MOSFET, and our range was within the MOSFET range.
Yeah, you're fairly low voltage.
Yeah. But yeah, it was all of this was based off research that we did from those papers.
What is the individual MOSFET rated at?
It's 220 volts maximum, 175 amps drain source, and we're going to use 4 of them in parallel, so it'll be able to sync 700 some odd amps, and we're going to be rating.
How are you going to promote current sharing between them?
They're each going to have their own individual drivers, and we're going to try to mount them, lay them out on the PCB as ideal as possible, with the same trace lines and everything like that. We haven't really gotten that far. We know we need to take that into consideration, but we haven't gotten that far in floor testing.
Thanks so much.